All right, this will be part one of the video because I don't think we're going to get as far as I would like today, and we're going to be off schedule, but it is what it is. So our next unit's all about acids and bases. So we'll do kind of the intro, which is review from unit 4, but we'll talk about it to make sure we've got it down, and then we'll start the pH scale, and then I'll probably finish that on Monday, so I'll send you the rest of the video that day. I'll get as far as I think we will potentially get in class today. That way you don't have to be on Zoom while we're doing it. All right, so quick review. So acids, remember, increase the concentration of hydrogen ions. So when you put them in water, and this will always be in water, they make H+ ions. It's kind of the generic definition. So HCl is a great example, hydrochloric acid, H+, Cl-, it's a strong acid, it completely ionizes, but the key is it makes H+. Okay. Bases, kind of the old school definition, increase hydroxide concentration. And so sodium hydroxide is a great example. We all better know by now that all sodium compounds dissolve in water and they dissociate into Na pluses and OH minuses. So again, this is what makes it a base. And so those are kind of your basic definitions. And we're going to spend most of the unit looking at the Bronsted-Lowry, which we did back in unit 4. But the key is you do make H pluses and OH minuses. That's still going to be the working thing for an acid and a base. And remember, we've got strong and weak. So strong things completely dissociate. And we'll look at K values for equilibriums with them, but they're going to have large K values. So again, that's going to tell us it's product favored. So like HCl in solution, none of them stay together. Everybody breaks apart. That's what we assume is going to happen. Is product favored. Essentially, all of them make ions. Weak, partially. I should say ionized. That was bad of me. Change that. Technically, it's ionizing because it's covalent. So weak, partially ionized, and this is where all the equilibrium stuff we did last unit is going to come into play. All right, so they're going to make some ions, but these Ks are going to be very reactant favored. So most of it is going to stay as the compound, which is why like in an equation we don't separate it, because in solution most of them stay as HF. Okay, so very little, and that's what we'll end up calculating, will turn into the hydrogen ions and the fluoride ions. All right, so we did Bronsted-Lowry back in unit 4, but a quick recap. So acids donate a proton, and remember a proton is an H+. So here's an example with NH3, and you always have to react it with something because you've got to have somebody to transfer it to, so we'll just generically go with water for right now. Nitric is one of your strong acids, so we do show it with a one-way arrow. Nitric acid will give away an H+ to the water, so now water will have 3 hydrogens and a positive charge, and then it'll be left with NO3 with a -1. Okay, so here's your acid. In that case, water acts like a base. NH4+, again, weak acid. It's weak, so we will show an equilibrium. It'll transfer an H+ to the water. You'll make H3O+, and then you'll make NH3. Okay. So this is kind of the key. Every time you have a Bronsted-Lowry, like where we're looking at acids, they're going to make H3O+. And H3O+ is called hydronium. And it does get used interchangeably with H+ a lot. AP prefers hydronium, but H+ will be acceptable when we start doing some equilibrium. I'll show you how that works. Bases accept a proton. So here, NH3 is a base. We'll just put it with water for right now. Since it's going to steal it from water, it'll steal an H+, so now it'll be NH4 with a positive, and it leaves the water as OH-. There's your clue that it's a base. CO3 2- can do the same thing. Again, it's a weak one. It's going to steal an H+. It'll make HCO3-, and again, the telltale sign that it's a base, we make hydroxide. Okay, so even in a Bronsted-Lowry definition, you're still going to make, typically make hydronium hydroxide if it's in water. And so those are in the water solutions. Just a couple of vocab words so that we're very clear if they use it. But a monoprotic acid only has one proton to donate. It's kind of what you're used to seeing. So like hydrochloric acid has one hydrogen. Nitric acid has one hydrogen. And there are some organic ones, so like acetic acid. They typically will pull this H out. That's the only H that's actually acidic. The other H's are bonded to carbon, and carbon is not electronegative enough for that hydrogen to be released in water. So only the one H, and it's typically the one at the front. I think you can figure out that polyprotic is going to mean it's got more than one it can donate. So you've got like sulfuric acid and carbonic acid. And those are technically called diprotic acids because they have two. And then you can obviously have three. Phosphoric acid has three. Just some key vocabulary. If we see them in problems, I want you to know what they mean. With bases, you can kind of do the same thing. You can have polyprotic bases where they can take more than one proton. They always are going to be the anions of those acids we just looked at. So like if it's a polyprotic acid, the anion, the polyatomic that's inside of it, can be a polyprotic base, and it can take more than one proton. So like carbonate, and we already wrote the first one, so it can take an H. It'll make H3O minus and OH minus. And then bicarbonate, which is what that one is called, can then also, in theory, act as a base and take an H from water. So you can have them where they can take more than one. And then last vocab that you should know, and we've already talked about this one too before we look at pairs, but amphiprotic or amphoteric are things that can act as either an acid or a base depending on what you mix it with. Now, I'm not going to do this one with water because deciding how it would act with water, it would be with K values, and we haven't done that yet. So we can have it as an acid, so we'll react it with a base. So we can take HPO4 2 minus, we'll do ammonia as kind of our generic base. It'll act as an acid, so it's going to give away the H+. So ammonia will take an H+ and become ammonium. PO4 will lose an H+ and be PO4 3 minus. As a base, if you put HPO4 2 minus with an acid, and I'm going to do a weak acid so it stays in equilibrium. We could do a strong acid, but weak acids are always two-way streets. Again, as a base, now it's going to take the H+ from the nitrous acid, so H2PO4 minus, and then NO2 minus will be left. So depending on who it's with, it can act as either an acid or a base. Things you need to recognize as amphoteric would be water, very clearly. We've done lots of those reactions. And then the like kind of middle of the road from your diprotic acids, so like HCO3 minus could give an H or take an H. Obviously, we just looked at HPO4 minus, H2 minus 2, H2PO4 negative 1 could do this, HSO3 minus. So there's all of those ones that come from diprotic acids. And last little review, and I feel like we did this back in unit 4, but I want to kind of make sure we talk about the words and the vocabulary. So you've got what we call conjugate acid-base pairs, and they're pairs of compounds or ions, and they're just different by an H+. So like HCl would be the acid, his base pair would be Cl minus. You could have acetic acid, and its conjugate base would be acetate. You can have a base, so ammonia, and its conjugate acid would be NH4+. So you've got differing by just an H+. In every reaction that we look at with Bronsted-Lowry acids and bases, you have two pairs, inside of it. And I'm pretty sure we did this back. I can't remember if we called them conjugate acids and bases. So on the left side, you're always going to have an acid and a base. And on the opposite side, whoever you can pair them with, your base will pair with its conjugate acid. Your acid will pair with its conjugate base. So we'll write an equation, and then we'll talk a little bit about the pH scale. All right, so it says write the balanced equation for the reaction between nitrous acid, so there's our acid, obviously, and ammonia, and there's our base. All right, nitrous acid will be the acid, so it's going to transfer an H+. So ammonia will become ammonium, and nitrous acid will be left as nitrite. So here's your acid. The guy on the other side of the equation that it pairs with should be NO3. They're differing by an H+, would be called the conjugate base. And then here's our base, and the one that it pairs with is our conjugate acid. And we do call acid and base on the reactant side, and it's conjugate acid and conjugate base on the right side, on the product side. And so just simple vocabulary words. That should all have been review. Now comes the pH scale. And this is where I don't know how much you all did with Mr. Kuhn, so we'll see. We'll just kind of do the basic pH scale, and then we'll finish it on Monday. So what water does, naturally, it's called the auto-ionization of water. So 2 water molecules, and you can write it as 2H2O if you want, in water can react, and one will act as an acid, one will act as a base. So we'll make 1 hydronium and 1 hydroxide. Now, you have to realize this is an incredibly reactant-favored reaction. So very few of them produce the ions. Okay? We can write an equilibrium expression. So K products on the top. And then reactants on the bottom, but both of our reactants are liquids, so we're not going to include them. So there's your K expression. They call it KW for water, so it's the K of water, is hydronium concentration times hydroxide concentration. And most of the time, we're going to use equals 1 times 10 to the negative 14th. So notice again, negative 14th, incredibly reactant favored. All right, we're talking very few of them turn into ions. So in water, that's why we always assume it's water. Not very many of them make ions. And this value is only true at 25 degrees Celsius. K's will vary with temperature. Right? And the AP loves that idea. So it is 1 times 10 to the negative 14th so long as you are at 25 degrees Celsius. That's the way AP prefers for you to write it, but you can also just write it with 1 water molecule making the ions. Right? And in that case, KW is H plus times OH minus. And you just have to realize that you can use H3O plus and H plus kind of interchangeably. All right, so it is acceptable to do it that way. And we do this with acids. I'll show you the 2 options. Again, AP prefers hydronium, but you can have H plus. So with that, in any aqueous solution, so water, if you are at 25 degrees, because it's, again, K makes a difference, in a neutral solution, and this is actually always true, neutral solutions, your hydronium is going to equal your hydroxide. And at 25 degrees, they both happen to have a value of 1 times 10 to the negative 7th. And we've done equilibrium before, so we can make a little ice table. We can talk about where that number comes from. So liquid won't matter. We'll assume these are both 0 before anything happens. All right, our water, we put it with water. It'll make this equilibrium. These will both go up by x. So at equilibrium, they are both x. Well, we know that KW equals hydronium times hydroxide. So So 1 times 10 to the negative 14th equals x times x, which is how we get that 1 times 10 to the negative 7th. But again, that's at 25 degrees Celsius. At other temperatures, K is different, and that would not be true. But what is always true, if your solution is neutral, these two are equal in concentration. That's what a definition of a neutral solution is. If your solution is not neutral, it's a variation of which one is in higher concentration. And this should make sense. Acidic solutions have more hydronium. Basic solutions have more hydroxide. Right? But in water, if you know the hydronium, you can always find the hydroxide. So we'll do 2 of those, and that's my guess of how far we'll get in class today. So find the hydroxide concentration for a solution with this concentration of hydronium, and again, it's at 25. So the Kw that we know is going to work. So Kw is hydronium times hydroxide. It's 1 times 10 to the negative 14th, and that for sig figs would be like an infinite. Hydronium is 8.7 times 10 to the negative 9th. And we can figure out, well, what would the hydroxide concentration be in that case? For some reason I don't have it worked out on my calculator. So we would do 1e negative 14 divided by 8.7 e negative 9. So our hydroxide concentration would be 1.1 times 10 to the negative 6. So we know both of their concentrations, and if you look at them, we can tell that this solution is basic because the hydroxide concentration is bigger than the hydronium concentration. All right, so here again, hydronium concentration, 25 degrees. And we can plug them in. Again, it's Kw, so 1 times 10 to the negative 14th will be our hydronium concentration times our hydroxide, which we don't know. So 1e negative 14 divided by 4e negative 3. That's really sad that I typed that in. I should be able to do that one. So there's your hydroxide. And then you can compare them, and very clearly the hydronium concentration is bigger than the hydroxide. And if that's true, it would be an acidic solution. All right, so the relationship of them is going to tell us whether your solution is acidic or basic.